We are starting, and let me recall that in the last lecture, I have introduced the Dirac equation. I basically discussed the physical principles which are standing behind derivation, behind the derivation of this equation. And we essentially introduced this equation for an object which is called spinor, and we have shown that the the main consequence of Dirac equation, as we have just computed, is that this equation also satisfies, as a consequence, it leads also to the satisfaction of the Klein-Gordon equation. In other words, every component of our spinor satisfies the Klein-Gordon equation, which means that every component describes a relativistic particle. That means the dispersion relation for this particle is a relativistic relation between energy and momentum. We have also seen that equation involves a set of matrices which satisfy the following properties. There are three matrices alpha I, which satisfy the following algebraic relation. So alpha I alpha j plus alpha j alpha I is equal to 2 delta ij. And there is one matrix beta for which we have the relation with matrices alpha I of the form alpha I beta plus beta alpha I is equal to 0, and in addition beta squared is equal to the identity matrix. And then we have shown that traces of all these matrices are equal to 0. So trace of any alpha I is equal to 0, as well as trace of beta. And also we have seen that the number of eigenvalues plus 1 is the same as number of eigenvalues minus 1. So the numbers of these eigenvalues is the same for these matrices. And therefore, these matrices can be realized in even dimension, only in even dimension, because only in this case they have a chance to have the same number of eigenvalues plus 1 as the number of eigenvalues minus 1. And before I continue, let me ask if you have some questions concerning the material we have discussed in the previous lectures. Okay, if you don't have questions, then I will continue. And now what we are going to do, we are going to ask about the concrete realization of these matrices. Do they exist? How we actually realize them in an explicit way? And so the first idea is that since matrices must exist only in even dimensions, let's try the minimal even dimension where such matrices have a chance to exist, namely dimension n equals 2. So suppose we are looking for these matrices as 2 by 2 matrices. And then we know that in 2 dimensions, so among 2 by 2 matrices, we have 3 distinguished matrices, which are Pauli matrices. So sigma 1, 0, 1, 1, 0. Sigma 2, which is 0 minus I, 0. And sigma 3, which is 1, 0, 0, minus 1. These matrices are Hermitian. These matrices are traceless, well, you see it explicitly from the form of these matrices. And they actually obey the desired relation, namely the anti-commutator of these matrices, sigma I, sigma j, is equal to 2 delta ij. And you see that this is the same as anti-commutator of matrices alpha I and alpha j. However, in 2 dimensions, the fourth independent matrix would be just the identity matrix. So identity matrix. But unfortunately, this cannot be identified with beta, because identity matrix would commute with Pauli matrices, while we should have a non-trivial relation between sigmas and matrix beta, which is not just a commutation, simple commutation relation. So this means that in dimension 2, we don't find such realization of Dirac matrices, of these alphas and betas. They do not exist for n is equal to 2. And then the next trial would be to ask for such matrices in dimension 4. And indeed, it appears that the minimal dimension where one can construct the 4 matrices alpha I and beta with all these properties above is 4. So concretely, you can take the following construction. You can take alpha i's to be 4 by 4 matrices, which I will write in terms of blocks as follows. So here I will write 2 by 2 block, which contains only zeros, another 2 by 2 block, which contains only zeros. And here I put Pauli matrix sigma I and another Pauli matrix sigma I. And for beta, I will take matrix 1, which is identity matrix, 2 by 2 identity matrix, and the -1 here. And then here zeros, like this. So you can check that these matrices do indeed satisfy all the relations above. And as you see, they are traceless. They are in even dimension. Their eigenvalues are 2 plus 1 and 2 minus 1. And well, they satisfy the commutation relations above. So that's explicit realization, concrete and explicit realization of the matrices which should feature in the Dirac equation. So just to repeat what we have found in the last lecture is that the Dirac Hamiltonian and the Dirac equation in the Hamiltonian form can be written in the following way. So I h bar d psi over dt equals to h psi, where h will be the Dirac Hamiltonian. I will call it first quantized Dirac Hamiltonian, meaning that here I will follow the kind of pedestrian approach to the theory where I treat psi as a wave function. Just like as we discussed was an initial idea of Schrödinger to understand Klein-Gordon equation as a Schrödinger equation for a relativistic wave function. Here it's similar. We understand psi as a wave function, albeit multi-component, for the Dirac equation, which has the form of the standard Schrödinger equation. Well, except with an exclusion that in this case our psi has now 4 components, and the Dirac Hamiltonian is matrix, which we can write in the following form. So alpha multiplied by momentum P plus beta MC squared, or in a, how to say, more explicit form, we take this H to be C alpha I, and Pi is minus I H bar d over dxi. So realization of the momentum operator by derivative plus beta mc squared. So this is matrix differential operator. Matrix differential operator acting on a 4-component vector psi. I don't actually want to use the word vector. I will call it multi-component wave function, or simply column. Psi 1, psi 2, psi 3, psi 4. Okay. Now, what we would like to do now is to investigate a bit further the algebra of the matrices which enter the Dirac equation. And this is needed in order to discuss covariant properties of this equation, particularly to understand how this equation transforms under Lorentz group. This Lorentz group is, of course, very important to us. It's a symmetry group of relativistic quantum field theory. And we have to understand how the equation we have introduced transforms under Lorentz transformations. And in order to do this, we have to better understand the structure of the matrices which enter our Dirac equation. And to do this, we actually take our Dirac equation and multiply it by the ratio beta divided by c. So beta is our matrix and c is the speed of light. And we introduce the new notation. So let's do the following. We identify beta with a matrix gamma with index 0, and gamma i's, I introduce gamma i's, which will be the product of beta with alpha I, where I is running 1, 2, and 3. And so doing that, let's also identify x0 with c d over d with ct. So d over dx0 is 1 over c dt. And then our Dirac equation can be written in a more symmetric form. So I h bar gamma 0 d over dx0 plus gamma I d over dxi minus mc multiplied by psi equals to 0. You see matrix beta disappeared, and before it was standing with mc, but then I multiply the equation by beta from the left and use the properties that beta squared is equal to 1, is equal to identity matrix. Then beta disappear, and this is how equation looks like. And even more elegantly, now you can use the relativistic definition of a scalar product, relativistic scalar product. So write it as I gamma mu d mu. So sum here runs sum over mu runs here through indices mu is equal to 0 and then 1, 2, 3 minus mc divided by H bar acting on psi is equal to 0. And very often in the books, you see that with a natural choice of units, H bar is equal to C is equal to 1. Then this equation takes the form I gamma mu d mu minus M acting on psi is equal to 0. And this is the Dirac equation in sort of final form we would like to study. Any questions here? That is an important form to remember, to have in mind, and understand. Okay, so now we can see also that with the new matrices gamma mu, the algebraic relations which we have introduced for alpha and beta can be also uniformized in one relation for matrices gamma mu, namely gamma mu plus gamma mu is equal to 2 eta mu multiplied by identity matrix. And so the free algebra generated by symbols gamma mu modulo this relation here, or subject to this relation here, is called Clifford algebra. Clifford algebra. The name goes back to the history, to Clifford, and this algebra has been known to mathematicians before the discovery of the Dirac equation, but miraculously it turns out that this mathematical background, which is behind, on which the Dirac equation is based on, actually already existed in mathematics in the form of this Clifford algebra. Now, from the definition of this matrices gamma mu, it is clear that matrix gamma 0 is Hermitian, so it satisfies the following relation: gamma 0 and then Hermitian conjugated is equal to gamma 0, so it's Hermitian, while the matrices gamma I, they are anti-Hermitian. So they satisfy this relation here. And you remember, this is because gamma I are given by the product of beta with alpha I. Beta and alpha I are Hermitian, but under Hermitian conjugation, we have to remember that we have to change the order of matrices. So we will have alpha I dagger beta dagger, alpha I and beta are Hermitian, but then we need to commute alpha I with beta, and that results in the minus sign, in the appearance minus sign, due to relation between beta with alpha I. So it gives beta multiplied by alpha I, which is minus gamma I. And so matrices gamma I, as a consequence, are anti-Hermitian. Now, these two hermiticity properties, they can be combined in one relation, which can be written in the following way. Gamma mu dagger is equal to gamma 0, gamma mu, gamma 0. You see that when mu is specified to 0, you will have here gamma 0 dagger, and then you have gamma 0, gamma 0, gamma 0, so 3 gamma zeros, but gamma 0 squared, due to this Clifford algebra relation, is actually equal to 1, and so then you have back to the hermiticity condition for gamma 0, and analogously for gamma i's. The same situation there for gamma i's. I forgot to mention that in this Clifford algebra relation, eta mu is Minkowski metric. standard Minkowski metric. Standard Minkowski metric. Now, another important observation is that actually we have found one concrete realization of our gamma matrices, which satisfies these Clifford algebra relations. But in fact, there exists an infinite number of possible realizations. And this can be recognized by noting that actually if we perform the following similarity transformation, so we take gamma mu and transform it in the way u gamma mu u minus 1, where u is an arbitrary unitary matrix. U is an arbitrary unitary matrix. Then the new gamma matrices obtained after this transformation, they will satisfy the same Clifford algebra relations and also the same hermiticity properties. Well, the fact that Clifford algebra relations are satisfied is trivial. So you take gamma mu plus gamma mu and multiply it from the left by u and by u minus 1 from the right. Then you see that this can be written as u gamma mu u minus 1 u minus 1 u gamma nu u minus 1. So I substituted identity in between, identity matrix in between, plus u gamma nu u minus 1 u gamma mu u minus 1. And so you have therefore here gamma mu prime, so transformed matrix, gamma nu prime plus gamma nu prime gamma mu prime. And what you have on the right hand side of this relation is just still 2 eta mu nu. And then since in the original Clifford algebra relations, on the right hand side of the Clifford relation, you have identity. So you have u minus 1, which is the same identity matrix. 2 eta mu nu identity. Okay. So the new gamma matrices obtained by this unitary transformation, they satisfy the same Clifford algebra relations. And you can also check in an analogous way that due to unitarity of u, hermiticity property of newly introduced gamma matrices are the same as for the old ones. Now, this representation, concrete representation, which I have introduced for alpha I and beta in terms of gamma matrices, read in the following way. So gamma 0 is the same as beta, and therefore it is 1, 0, 0, minus 1, while gamma i's are given by 0, sigma I, minus sigma I 0. And this representation of this concrete representation of gamma matrices in which gamma 0 is diagonal, this concrete representation is called Dirac representation. Is Dirac representation. So Dirac representation is a representation in which gamma 0 is diagonal and has this form 1 minus 1. No, and then gamma matrices, gamma i's are given by this block Pauli matrices of diagonal Pauli matrices. One of them comes in the lower block with a minus sign. So this is Dirac representation. But as I said, you can obtain other representations by applying, for instance, to the Dirac representation, the unitary transformation with arbitrary u. Now, let's investigate properties of our gamma matrices in more detail. From matrices gamma mu, from these matrices, you have construct 16 linearly independent Hermitian matrices. One can construct from gamma mu, one can construct 16 linearly independent Hermitian matrices. In the following way. First of all, you see that you can build up identity matrix. Identity matrix 1 is simply if you take eta mu mu, gamma mu, where mu, there is no summation over index mu, no summation of index mu. So take index mu to be either 0 or 1, 2, and 3, and then you see that from Clifford algebra, you just take in product of gamma matrices with the same index and multiplying it with Minkowski component of the Minkowski metric, you will just obtain identity from the Clifford algebra relation. So identity matrix is reproduced. Now, then you have 4 Hermitian matrices. Gamma 0, we know that it's Hermitian. And then gamma i's, if you multiply them with I, then they give you also Hermitian matrices with I running 1, 2, 3. So 4 Hermitian matrices obtained just from the original gamma matrices. Then you can build up 6 matrices, which I denote as sigma mu nu. And they will be given by the following formulas. So sigma ij are introduced as I, gamma j minus gamma j, j gamma I. So anti-commutator of gamma matrices divided by 2, which essentially due to the Clifford algebra relation, you can see that it's the same as I gamma j. And this is for I less than j, where I and j run in 1, 2, 3. And sigma 0 j are given by gamma 0 gamma j minus gamma j gamma 0 divided by 2, which is again due to the Clifford algebra relation. This is the same as gamma 0 gamma j. Also for j is equal to 1, 2, and 3. And then if you count these matrices, you will see that their number is equal to 6. So they are skew-symmetric in indices mu and nu. And therefore you have 4 multiplied by 3 divided by 2, so 6 matrices in total. 6 matrices in total. They are skew-symmetric in indices mu and nu, and explicitly introduced by means of these formulas, which are essentially the product of 2 gamma matrices. Then there is one important matrix. It has a special name. It's called gamma 5. One matrix gamma 5. Again, 5 stands here for historical reasons. Introduced as I gamma 0, gamma 1, gamma 2, gamma 3. So in other words, it's a product, essentially it's a product of all gamma matrices, of all 4 gamma matrices. No, and I is added here to provide the hermeticity property for gamma 5. So gamma 5 would be then Hermitian. And finally, there are also 4 matrices. Tau mu, introduced in the following way. So tau mu is tau I given by gamma I, gamma 5, where I runs 1, 2, 3. And matrix tau 0, which is I, gamma 0, gamma 5. Again, these matrices are Hermitian. And now that is all. If you count the total number of matrices we have introduced, there should be 16 of them. Indeed, we have 4 matrices here. We have 6 matrices, so in total 10 plus 4, these 14, plus 1 matrix 15, and the identity matrix 16. So in total 16 Hermitian gamma matrix, 16 Hermitian matrices constructed with the help of gammas. Let me also note that this gamma 5 we have introduced in this way, it satisfies the properties that if you take a square of it, then you will obtain identity matrix. And as I said, it is Hermitian. So these are the properties. And in the Dirac representation, so if you substitute gamma 0, gamma 1, gamma 2, and gamma 3 in the definition of gamma 5 by using the Dirac representation, then explicit form of gamma 5 in the Dirac representation is 0, 1, 1, 0. So this matrix then is off diagonal, is explicitly off diagonal. So in Dirac representation, gamma 0 is diagonal and gamma 5 is off diagonal. Now, you can check that all other possible products of gamma matrices and their linear combinations can be expressed where these 16 Hermitian matrices we have introduced by means of linear relations. So this means that these 16 matrices provide the basis in the space of 4x4 Hermitian matrices. And I mean, to finish this, the proof of this statement that indeed they form a basis, I need to show that they are actually linearly independent, that these matrices I have introduced are linearly independent. This can be done in the following way to show linear independence. First, you may notice that all these matrices, except identity matrix, they have vanishing trace. Now, about the 4 gamma matrices, that's something which we have already, well, let's see it, for instance. Let's do it for gamma mu. Take trace of gamma mu and use the fact that if you consider gamma nu, so one matrix gamma will have lower index nu and another is upper index nu, and we take no summation over index nu, then this is actually due to the Clifford algebra, such product of gamma matrix with low and upper index, according to the Clifford algebra, is equal to 1. Is equal to 1. Indeed, if you look at the Clifford algebra relation, gamma mu plus gamma mu is equal to 2 eta mu multiplied by identity matrix, you see that if I low down index mu, say let's do it with index mu, then I will have here on the right hand side lowering down of Minkowski metric gives me just a Kronecker delta. It will produce for me here Kronecker delta mu nu multiply with identity matrix. And now if I take index mu equals to index nu, I will get twice the same product gamma nu, and I'm not summing over index nu, no summation here, equals to 2, and then delta mu delta nu, it's 1, multiply with identity matrix, from where you see that these two cancel, and you just get gamma nu is equal to identity matrix with no summation, with no summation over nu. For any nu, you have such a relation. Now, coming back to the trace of gamma mu, I then use the following standard trick to prove that this trace actually vanishes. So take trace of gamma mu and plug inside the identity matrix in the form gamma nu. For index nu chosen to be not coincident with index mu. And then this I can write as a 1/2 trace gamma nu, and then gamma nu, and then under trace I can use its cyclic property and move gamma nu around to the right hand side, and then I will get here gamma mu, and I have the one and same expression twice, and so I need to divide it by 2 in order to reach an equality with the previous expression. So this is the way how I manipulate this product gamma nu under the trace. And then due to the Clifford algebra relation, since index nu was chosen not to coincide with index mu, then this sum here, due to the Clifford algebra relation, is actually 0. So the result is 0, which shows you that trace of all gamma mu's is equal to 0. And analogously, you can show that traces of all other matrices are 0. In particular, trace of gamma 5 is 0. And in the Dirac representation, you of course see it explicitly from the form of this matrix. Now, the fact that traces of all these 15 matrices, well, trace, of course, of identity matrix does not vanish, but trace of the remaining 15 matrices vanish. This can be used to show that these 16 matrices are linearly independent. This can be shown by assuming the opposite. So suppose these matrices are linearly dependent. Then if I make a linear combination of all of them, so I take A multiplied coefficient, some coefficient A multiplied by identity matrix, plus B mu gamma mu, plus C mu nu sigma mu nu, plus G mu tau mu. So I'm taking linear combinations of these 16 matrices with arbitrary coefficients. First with arbitrary coefficients. Then the statement that these matrices are linearly dependent means that I can have this linear combination to be equal to 0. So F is 0 with some non-zero for some non-zero coefficients. So in other words, there is a linear combination, then non-trivial linear combination, which relates these matrices, these 16 matrices. And the goal is to show that this is not possible. Then F is equal to 0 implies that all the other all the coefficients here in this linear combination are actually 0. This can be done in the following way. First of all, you take a trace of the left and the right hand side. And since on the left hand side f is 0, so trace of 0 is 0, so you get 0. On the right hand side, trace of any of these matrices, gamma mu, sigma mu, tau mu, gamma 5 is 0. And so you're left with A multiplied by trace of identity matrix, which is not 0, of course. It's equal to 4, so you get 4 multiplied by A. But then since you have 0 on the left-hand side, from here it follows that A must be equal to 0. And so this term is absent. And then what you do, you take this expression again for F, now without identity matrix, and you multiply it with gamma matrix, with some gamma matrix gamma nu. So you multiply it with gamma nu F. Again, you take a trace. So on the left-hand side, F is 0, and you get 0. And then you take a trace. Maybe I have to write here gamma lambda. And then you take a trace on the right-hand side. So trace of B mu gamma lambda is gamma mu plus C mu nu, trace of sigma mu with gamma lambda plus d mu, trace of gamma lambda with tau mu, and finally E, trace of gamma 5 multiplied with gamma lambda, like this. Now you can show by analyzing these traces here that all of them again are equal to 0, except this one. So this is not equal to 0. For mu is equal to lambda, you will see that this is not equal to 0 because due to the Clifford algebra, this will be proportional. Product will be proportional to identity matrix. And again, in this way, you will find that all coefficients B mu are equal to 0. And in this case, then you get rid of this term. And then multiplying the rest by gamma lambda, gamma beta, again, you take the trace and you show that coefficients C mu nu are equal to 0. And then the same is for D mu, and then finally for E. And so in this way, proceeding similarly to what I have explained, you actually show that all the coefficients in this linear combination, they must be equal to 0. And therefore, these matrices are linearly independent. So this means that the matrices we have found form a basis in the space of all complex 4x4 matrices. If you allow the combinations, linear combinations of these 16 matrices with complex coefficients, so linear combinations of 16 matrices we have introduced, linear combinations of 16 matrices with complex coefficients, allow you to reconstruct any complex 4x4 matrix. To reconstruct any 4x4 complex matrix. So this statement is very similar to what you have in 2 dimensions with the Pauli matrices. If you have 3 Pauli matrices and identity matrix, and you consider all linear combinations of those with complex coefficients, you can expand over these linear combinations with, you can expand over these Pauli matrices and identity matrix with complex coefficients, any complex 2x2 matrix. So the same we are proving here, analogous statement we have here, where we say that any complex 4x4 matrix can be expanded over a linear basis of 16 Hermitian matrices constructed from gamma matrices with complex coefficients. Okay, so that's an important statement. And now I think I'm ready to come to the discussion of transformation properties of the Dirac equation under Lorentz transformations. Do you have any questions here? This is some important facts I told you about the Clifford algebra. And now we are coming to the discussion of Lorentz transformations. Yes, please.
Professor, I have a question related with the fact that these gamma matrices are not unique. When we write down the Lagrangian of this theory, we can extract some symmetries from this fact and some conserved currents for the fact that the gamma matrices are not unique. We can make a unitary transformation. We can extract some current.
This is not related to the fact that gamma matrices, I mean, symmetries, they do exist. Yes, for the Dirac theory, we will study the symmetries which are important, of course, and which lead to conserved quantities. But this is not related to the fact that gamma matrices are not unique. This is gamma matrices define you. It basically, this is a statement that you can pick up any representation of gamma matrices to write down the Schrödinger equation, to write down the corresponding Dirac equation. You can pick up any. It means that nothing should depend on the choice of a concrete representation. None of physical quantities you derive should depend on the way how you represent these gamma matrices.
Okay, thank you.
Because you see, if this would depend, then you would have, if physical quantities would depend on this, then you would have a trouble, because then you would have many different Dirac equations. You can write Dirac equations in many ways, and they would lead you to different physical predictions. So this is, of course, not acceptable, because after all, these gamma matrices are just numerical matrices. So they are numbers. There are certain numbers you put to formulate your equation, and then it suddenly turns out that from these numbers somehow you get different physical predictions. That would not be acceptable.
Okay, thank you. But then when you write down the Lagrangian of this theory, this cannot be a symmetry, right?
Yeah, that would mean that transforming gamma matrices to another set of gamma matrices would be equivalent to transforming the wave function, this psi, by unitary transformation. And unitary transformations, they are always allowed in quantum field theory and quantum mechanics. You know, quantum mechanics allows for unitary transformations which do not change the probabilities. And this is the same statement as we have here. Changing the basis of gamma matrices can be compensated by the change of the wave function. And you see it from the Dirac equation. How do you see it? You write an equation as I gamma mu d mu minus m, say, natural units. You have this equation here. Now imagine you multiply, or you pass to another basis. So you say, well, I change my gamma matrices by u gamma mu u minus 1. For unitary matrices, u minus 1 is the same as u dagger. So this is u gamma mu u dagger. And then in the new basis of gammas, you will get here u gamma mu u dagger d mu minus m acting on psi. This would be your new equation. But then you see what happens here is that since matrix is unitary, you can write it as U gamma mu U dega d mu minus M U dega, because U dega is just an identity matrix, the same as standing here. And then you take this equation and multiply it from the left by U minus 1. Multiply it from the left by U minus 1. So U then cancelled on the left-hand side. And this U dega and this one, you put close to psi. So your equation now, then after this manipulation, will look like I gamma mu d mu minus M multiplied with identity matrix, acting on U dega psi is equal to 0. And then, in fact, what you see is that you return back to the original form of the Dirac equation, where you perform on your wave function psi a unitary transformation with the matrix U. So it's like new psi prime, where psi prime is just U dega psi. And unitary transformations are allowed. This is a wave function. In our treatment, in our sort of first quantized language, this is a wave function. And the change of the wave function by unitary transformation should not result in the change of the probability. So it's the same as quantum is in quantum mechanics, unitarity of quantum mechanics.
Thank you very much.
And so this is very nice what we have here. This indeed should mean that nothing should depend on the way we represent these gamma matrices. The important question, which you may study actually during the seminars, is the following question. Is it true that in 4 dimensions, any representation of gamma matrices is unitary equivalent, for instance, to the Dirac representation? In other words, if there exists another representation of the Clifford algebra, let's call it gamma mu prime, such that there is no unitary matrix U, for which U mu prime would be U gamma mu U minus 1. In other words, you can say, is it true that in 4 dimensions, there are no different equivalence classes of gamma matrices by equivalence, by unitary equivalence defined with the help of a unitary matrix U? In other words, if this is true that all gamma matrices which realize Clifford algebra are unitary equivalent to the Dirac representation. Okay, so that's an interesting question. I told you that if you have gamma matrices realizing Clifford algebra, then making a unitary transformation, you will get another representation of the Clifford algebra. That is okay, but I'm asking now a question, if this is possible to find a representation of the Clifford algebra which is not unitary equivalent to a given one. Suppose you give one representation of a Clifford algebra and then I give you another. And then the question is there is always exist a unitary transformation by means of which these 2 arbitrarily chosen representations are related? And the answer is that in 4 dimensions, there is only one class of unitary equivalent gamma matrices. So all gamma matrices which satisfy the Clifford algebra and which are Hermitian, which satisfy this hermiticity properties. So gamma 0 is Hermitian, gamma I is anti-Hermitian. They can always be related by means of a unitary transformation. There are no different classes you can construct, unitary classes which you can construct. There is only one class, so all representations, all different representations of the Clifford algebra They are always related by unitary transformation. It's a theorem. It's called Pauli theorem, and there is a chance that you will discuss this Pauli theorem in your exercise class. And I recommend you to ask to do this in the class. Okay? That's important statement. Otherwise, you would have in 4 dimensions different inequivalent Dirac equations.
So in 4 dimensions, there's only one class. So what about in higher dimension, like
in higher dimensions,
4?
it might be different. You might have inequivalent representations, and that would lead to construction of different theories.
Okay.
But since we are living for the moment in 4 dimensions, as the experience shows us, and for us, it's an important statement.
Yeah, so it's just about the theory, like string theory, there are many.
Yeah, exactly. So if you go to other dimensions, then you have to be careful, and you have to look at possible classes of inequivalent gamma matrices. In other words, in Pauli's theorem depends on the dimension. So you need to prove it every time you go there and you study representations of the Clifford algebra. So the general question which you have to study is a question about representations. Representations means the way you realize your gamma matrices by means of concrete matrices. So you study representations of Clifford algebra in general in various dimensions, in various space-time dimensions. So that's a general question. There is a classification of representations of Clifford algebra for any dimension. You can find it in the literature. Of course, this is a very well-studied subject, and I refer you to the literature, especially if you go to study string theories, and the knowledge of representations of Clifford algebra is very important there. Okay.
Professor?
Mm-hmm.
Sorry, I didn't understand this. If there is no U unitary transformation, then how are we writing this gamma dash mu equal to U gamma mu U inverse?
Sorry, say it again. Yeah. What do you mean how we write it? We pick up one gamma mu, representative gamma mu, we take up any unitary matrix, and we simply multiply from the left and from the right gamma mu from the left by U and from the right by U minus 1. And we get new gamma mu primes, which satisfies the same Clifford algebra relations. Is it your question?
No, then what is that? There is no unitary transformation also to U.
No, there is a unitary. There is a, take any unitary matrix, any. Do this transformation with any U. The unitary matrix always exists. In 4 dimensions, you have infinite number of unitary matrices. They form a group, unitary group of 4 by 4 unitary matrices. All matrices satisfying the relation U dega U is equal to identity matrix. Yes. Take any of them, any. Make such a transformation on gamma mu. And then you will find gamma mu satisfying absolutely the same relations as the original matrices gamma mu. Maybe I don't understand your question.
You have written here that there is no unitary transformation.
No. I'm not saying there is no U. I'm saying that all gamma matrices which you can have realized in the Clifford algebra are related to each other by some unitary transformation.
Okay, so there exists unitary transformation. Then what is that there not exists unitary transformation? As from the statement, I see.
Once again, unitary transformation like this defines an equivalence class. You can say that your matrices U mu prime and U mu, gamma mu prime and gamma mu belongs to the same equivalence class, belongs to the same equivalence class. That means that they are equivalent if there exists a matrix U, which is unitary matrix U, such that gamma prime mu is equal to U gamma mu U minus prime. Okay? Then we say that these matrices are unitary equivalent because there is a unitary transformation which transforms one set of gamma matrices to the other set. The question which I may ask is that if in 4 dimensions there exist different equivalent classes. Equivalence classes, equivalence splits the whole possible space of gamma matrices into equivalence classes which are non-intersecting, which are disjunct. So if you pick up gamma matrix here and gamma matrix from another class, set of gamma matrices from one class into another class, within its class, all matrices are unitary equivalent, and within the other class, all the matrices are unitary equivalent, and so on. But since they belong to different classes, there is no unitary transformation which transforms matrices from one class to matrices to the other class. And my statement is that in 4 dimensions, there is no such a picture. There is a unique class. So all gamma matrices are unitary equivalent. So whatever representation of the Clifford algebra you construct, there will be always a unitary transformation which transforms this particular representation, for instance, to the Dirac representation we have introduced. So all gamma matrices are realizing Clifford algebra are unitary equivalent. So in other words, one set you can choose to realize Clifford algebra, let's call it gamma pool prime, is always unitary equivalent to another set gamma mu. There will be always a unitary transformation relating this set of matrices. Okay, is it clear now what I meant?
Yeah, I think it's clear. I have to study about this.
No, once again, I'm happy to explain this better. I just need to understand what is exactly sort of the point you would like to understand here. Once again, you can have many possible choices of gamma matrices to realize Clifford algebra. And later I will write you other ways, other representations of Clifford algebra in terms of concrete matrices. But again, what is important is all these different ways, all these different representations which realize these Clifford algebra relations, they are related to each other by some unitary transformations. There is always a unitary transformation which will transform one set of such matrices into the other set. You see, there could be a situation where there is no such a transformation. You find one set realizing these relations and another set realizing these relations. And then you see that there is no unitary transformation which relates one set to the other. And I'm saying that this is not the situation. The situation is that you always will find a unitary transformation which will transform one set into the other. That is exactly what I mean.
Yeah, it can transform within its own set, but it can't transform to the other set.
Sorry? Yeah?
It can transform to its own set, but it can't transform to other set.
Yeah, but the other set does not exist. So basically in 4 dimensions, there is only one set. So all matrices are unitary equivalent. All representations of Clifford algebra are unitary equivalent. That is a statement. So you give me two different sets, they both realize Clifford algebra, then I will find for you a unitary transformation which relates them. There is always unitary transformation which will relate them. They always unitary connected.
Yeah, so there is only one set, no disjoint set here associated with this.
Exactly. There is only one set. There are no such a situation where you have classes, different classes, not related to each other by unitary transformation. There is only one class. In other words, all gamma matrices realizing all representations of Clifford algebra are related to each other by some unitary transformation.
Yeah, okay, yeah.
Mm-hmm.
Thank you,
And
Professor.
this is very good. This is very good because it tells us that in fact, in reality, we have just one way to write the Dirac equation. We have one theory. And this is, of course, quantum electrodynamics at the end of the day, which we know.
But
now,
for example, if we have like isometries, then will it change?
which isometries you mean?
Of space-time?
The isometries of space-time are Lorentz transformations, or more generally Poincaré transformations. And that's exactly what I'm going to discuss now. So under these transformations, we actually have to understand what happens to our spin-up psi. Spin-up psi is, of course, a function on space-time. So remember, so psi, what is psi? Psi is, psi is a function on space-time. So psi is a function on x, and psi is explicitly, it's a four-component object. So it consists of four functions on space-time. Now the question which I would like to understand is what happens to this psi under P-Fermi-Lorentz transformation? That's exactly the question I want to address now. And we know that all Lorentz transformations, they form a Lorentz group, and our Lorentz group has four different components. And one component which contains identity is a subgroup of the Lorentz group. It's a subgroup which contains proper orthochronous transformations. And the other components of the Lorentz group are obtained from this one by means of parity and time reversal operations, right? So remember, there was four components. One component was proper orthochronous Lorentz transformations, and then there were other components which could be obtained from this one by implying either parity or time reversal, or combined parity with time reversal. Parity and time reversal. And so what we will do then, we will first understand how our spinor transforms under proper orthochronous Lorentz transformations, which form a subgroup of the Lorentz group. And then we will see how the spinor transforms under parity and time reversal. And in this way, we will understand how it will transform under the full Lorentz group. Now, under proper Lorentz transformations, we know how the variable x transforms. So x is a space-time coordinate, and under Lorentz transformations, it undergoes the following change. So x prime mu is lambda mu nu multiplied with x nu, where this lambda mu nu is a matrix of Lorentz transformations with a defining property that eta mu nu, lambda mu alpha, lambda nu beta is equal to eta alpha beta. That's a defining property of the Lorentz transformation, which actually tells you what Lorentz transformation is. Lorentz transformation is a linear transformation of space-time coordinates, which preserves the Minkowski metric. And this is exactly what is written down here. Now, it is very natural to assume that what happens under Lorentz transformation is that our wave function psi x goes to psi prime depending on the transformed point x prime, which is related to the old function psi on x by means of application of some matrix S, which we don't know, but which we need to find, acting on psi on x. So S here is some matrix, and this matrix must be a function of the transformation lambda we apply to transform space-time points. So this is the same lambda as making our x to x prime. And so this matrix S we need to find. And this can be done by applying the relativity principle. Yes, relativity, Einstein relativity principle. This is a general principle which we apply to all equations of physics, saying that in the new Lorentz frame, the Dirac equation must look the same in the original frame as in the original frame. Namely, after we do this Lorentz transformation, our new function psi prime x prime, as we see it from the new frame, must still satisfy the same Dirac equation: I gamma mu d over dx prime mu minus mc over h bar. I write complete equation with all the parameters. Psi prime on x prime is equal to 0.
Well, sir,
So you see,
this
yeah.
can also be observed from the fact that they are all scalars, right? So they will be invariant.
They are not scalar. So this function is not scalar function. It's not scalar.
Oh, yeah.
It's not scalar. You see, it has 4 components. It's a spinor. It's what we call spinor.
Yeah.
And the fact that it's not a scalar, a spinor, is exactly the way that this object, scalar and spinor, transform differently under Lorentz transformations. What we try to implement here is a relativity principle, which tells us that equations of physics should look the same independently on the Lorentz frame in which you write them. So, for instance, if you make a Lorentz transformation with respect to the frame of me, we still should agree on what we call Dirac equation.
Right.
So Einstein relativity principle basically is a principle which generalizes Newton's relativity principle to the case of relativistic invariance. It takes into account the fact that the speed of light is finite constant, which is independent on the reference frame in which you measure the speed. And as a consequence, it tells you that equations respecting relativistic invariance, exactly in these words, respecting relativistic invariance means that they should have the same form in any Lorentz frame. So in other words, if you do a Lorentz transformation from one frame to the other frame, the wave function should transform in such a way that in the new frame, the equation for the transformed wave function will have the same form as in the old frame. This simply means that Lorentz transformation is a change of coordinates, which should leave the form of your equation covariant. Covariant means exactly what I'm writing here. So you just put primes on all the coordinates, and otherwise equation looks the same as in the original frame. Just change of coordinates which keep the form of your equation the same. It's what it means, covariance. It does not mean exactly invariance. Invariance would mean that in the new frame actually nothing depends on primes. So equation is invariant. It means it looks absolutely the same. But here we require covariance. It means that in the new frame, all what happens is that I put on my quantities primes. And primes mean, here you see that I'm now measuring the coordinates with respect to the new frame. So x prime is a coordinate, but taken with respect to the new Lorentz frame. So that's principle which we always require in quantum field theory from our relativistic equations is a relativity principle, and we just apply the same relativity principle to the Dirac equation. And this will help us to actually understand how then psi prime x prime should be related to psi and x. And we, in this way, establish this matrix S, depending on the transformation, on Lorentz transformation, which should do this job, which should transform the wave function from one Lorentz frame into the wave function in the other Lorentz frame.
Yeah, Professor.
Mm-hmm.
This means it is without potential, right?
Without, yes, so this is what we call free Dirac equation. It's just an equation for spin up psi without, say, interacting of psi with anything else, most importantly with electromagnetic field. But later on, we introduce the Dirac equation in the presence of electromagnetic field.
So after that, if we introduce in potential term, then the form might change.
No, potential, by potential, what do you mean? Potential, yes, if you put an external field, so that means potential, yes, there will be additional terms in this equation. Additional terms. But these additional terms will not change the relativity principle. Relativity principle is universal. It's applied all the time. And the transformation which we obtain for wave function from this equation, they will stay whatsoever, whatever you will add extra terms describing interaction of psi with any other fields. Other fields also should transform according to the relativity principle.
Okay.
So relativity principle, once again, it's universal principle which tells you that the laws of physics should look the same up to the change of coordinates in all Lorentz frames. They should look the same, like I'm writing here.
Yes.
It is exactly the principle of relativistic covariance, if you wish. This is relativity principle. You can say it's a principle of relativistic covariance of your equations under Lorentz transformations. So, to proceed, what I want to do with this equation, I want now to return back to the original form of the Dirac equation, which would allow me to relate psi prime or x prime with psi on x. And to do this, I need first to look at derivative, d over dx mu. So what is this? I can write it as a dx prime over d nu, d over dx mu, d over dx prime nu. So this is a change of coordinates, a transformation of derivative under the change of coordinates. And then x prime nu over x mu, this derivative, you see, this is this expression here is found from this formula here. So all what I need to do, I need to differentiate x prime given by this formula. And you see what I will be getting then is lambda nu mu d over dx prime mu. So this is a way how derivative with respect to old coordinate and the new coordinate are related. This is the way they are related. And if you wish, you can invert this relation and write the following formula. So lambda minus 1 inverse Lorentz transformation, nu mu applied to d over dx nu gives you d over dx prime mu. Yeah, so this relation of derivatives under Lorentz transformation. This is what follows from here by multiplying both sides of this equation with an inverse matrix lambda minus 1. Okay. Now, what do we do? We take this equation here, equation in the new frame, and multiply it from the left with the matrix S minus 1. Multiply from the left with S minus 1. What do we get in this case? We get I S minus 1 gamma mu S. Let me first write without substitution of dx prime mu minus mc over h bar, and then I will substitute psi prime on x prime as s psi x, and s minus 1 from the left cancels with s, and so I will just get here original psi on x equals to 0. So this is what I have, and then let me now substitute the change of the derivative. So I s minus 1 gamma mu s prime, and now I substitute lambda s minus 1 gamma mu s, and now I substitute the change of the derivative. So lambda minus 1 nu mu d over dx nu minus mc over h bar acting on psi on x is equal to 0. So you see that I will reproduce the old form of the Dirac equation, so Dirac equation in the original frame, if I impose the condition s minus 1 gamma mu s multiplied with lambda minus 1 mu, let me see here, I will put here index nu, summation index change a little bit. So nu mu nu is equal to gamma mu. Here you see I'm summing over this index here, the summation, and then there is this index nu. And now to compare it to the standard form of the Dirac equation, what I'm doing here, allow me to use my eraser just to change the dummy index, summation index mu for nu, and the index nu, the old one, which is also a dummy summation index for mu. And then this equation I compare to the old form of the Dirac equation. So let me do it in detail. So I want to compare this to I gamma mu d over dx mu minus mc over h bar psi on x is equal to 0. So you see that these terms coincide. These derivatives I do have. Here I have gamma mu, and here instead of gamma mu, I have this combination here. So you see that then these two equations will coincide if I impose the following condition: s minus 1 gamma nu s multiply with lambda minus 1 mu nu. If this is equal to gamma mu, then I am back to the original form of the Dirac equation. And then relativistic relativity principle will be satisfied. So this means that matrix S, which I'm looking for, is a solution to this equation. So I need to understand how to solve this equation and find how S is related to lambda. From this equation, I mean, you can multiply it by matrix lambda from the right and bring it to the form S minus 1 gamma mu S is equal to lambda mu nu multiply with gamma nu. Or another way to write it is to multiply this original equation, this one, by S from the left and by S minus 1 from the right. And also, then it will lead to another form, S gamma mu S minus 1 equal to lambda minus 1 mu nu gamma nu. So you see this, you can say that basically what you do here, you see that you are transforming the index nu as the index of a vector with matrix lambda, the same as index of a vector should transform under Lorentz transformation. But this should be reproduced, should be compensated by acting on gamma mu with the matrix S by similarity transformation. And one needs to find the matrix S, which does the Lorentz rotation on the indices of gamma matrices by means of similarity transformation. And so this S we need to find. Now, to do this, it's very convenient to come to the infinitesimal form of this equation. So by assuming that our Lorentz transformation is close to identity, in other words, there exists a small parameter, let's call it epsilon, and so lambda mu nu we consider is a function of epsilon, of this small parameter, and then we expand it in powers of epsilon, and so the first term is an identity, and then the next term I will write in the form epsilon multiplied by eta mu rho omega rho nu plus where omega rho nu is a infinitesimal generator of Lorentz transformations. Infinitesimal generator of Lorentz transformations. And eta mu nu Minkowski metric here raises the index of rho, and I introduce it just for convenience. You see here indices of lambda on different level. Mu is up, nu is down, and then for Lorentz generator, I raise index one of lower indices up with the help of the Minkowski metric. So then we can actually find what are these omegas in this equation by just taking the defining relation for Lorentz transformation. So I take the relation eta mu nu lambda mu, let's write alpha here, lambda nu beta. Now these are functions of epsilon, and this is eta alpha beta. And I expand this relation in epsilon and keep only, will keep only terms of linear order in epsilon. So explicitly, this is what I need to do, is substitute delta mu alpha plus epsilon eta mu rho omega rho alpha plus For the second lambda, the same, delta nu beta plus epsilon eta nu tau omega tau beta plus equals to eta alpha beta. Then expand this in epsilon, left-hand side, and keep the leading term in epsilon. And then you will see that equation on omega, which you will get. So the leading term on the left-hand side will be equal to the leading term on the right-hand side. And this is eta alpha beta. So there will be cancellation of these terms. And then at linear order in epsilon, you will find the relation omega mu nu is equal to minus omega nu mu. So it simply means that this generator of Lorentz transformation with lower indices is simply a skew-symmetric matrix. Skew-symmetric matrix. Mu and nu run values 0, 0, 1, 2, 3. And so such a skew-symmetric matrix then has 6 components. So 4 multiplied by 3 divided by 2, 6. And these are exactly 6 Lorentz transformations forming, making all parameters, 6 parameters of Lorentz transformations, 3 rotations and 3 Lorentz boosts. So omega mu nu are, in this way, you can say these are infinitesimal parameters of arbitrary Lorentz transformation, including 3 rotations and 3 Lorentz boosts. Very good. So then I need to use a relationship between a Lie algebra and its Lie group. And what I want to do is to say that with this construction, I may write down the representation of the one parametric subgroup of the Lorentz group by simply exponentiating the Lie algebra element representing my Lorentz transformation, so omega multiplied with eta, and I will say what I mean by this, multiply with epsilon. So this exponential will give me a one parametric subgroup of the Lorentz group, where this parameter of this one parametric subgroup is exactly this epsilon. And by eta omega, I simply mean a matrix. So by definition, this matrix with indices mu and nu. And this is the one which I have already introduced. So mu rho omega rho nu. So this is one parametric subgroup of a Lorentz group. Now, this means that my original equation, which I want to solve, can be now written in the following way. So S minus 1, depending on epsilon, gamma mu, S on epsilon, is equal to lambda mu nu, depending on epsilon, gamma nu. So I write this equation by picking up as a Lorentz transformation these elements of the one parametric subgroup of the Lorentz group. When epsilon is equal to 0, I will get identity matrix. And therefore on the right hand side I will get gamma mu. And so I need to have, when epsilon is 0, also gamma mu on the left hand side, which means that this matrix S we are looking for must satisfy the property that when epsilon is 0, then it's just an identity matrix. And my further strategy will be to find a differential equation for S with respect to this parameter epsilon, and then solve this differential equation And in this way, to find what exactly this matrix S is. And to this end, what I will do, I will just differentiate now this equation with respect to epsilon. So differentiate over epsilon. So what you will get is minus S minus 1 ds over d epsilon S minus 1. So this is what I'm doing here. It's a derivative of S minus 1 on epsilon over d epsilon. This is this term minus S minus 1 ds over d epsilon S minus 1. Then there is gamma mu multiplied by S. Gamma mu multiplied by S. Plus, now I do not touch S minus 1 gamma mu, but I differentiate S. And this is a derivative of the left-hand side. And on the right-hand side, I will get d lambda mu nu over epsilon over d epsilon multiplied by gamma nu. Now, this relation further can be written in the following way. So if I introduce the variable, auxiliary variable x, which is by definition ds over d epsilon multiplied with S minus 1, then this equation here can take the following form. Gamma mu with x equals to d lambda mu nu over d epsilon S gamma nu S minus 1. So in other words, what I'm doing here, I'm taking this equation here and multiply it by S from the right and by S minus 1 from the right and S minus 1 from the left. And then the left-hand side reduces to a commutator of gamma mu with such x. And the right-hand side, it's what I'm writing down here. S gamma nu S minus 1 comes from these multiplications. And then this S gamma nu S minus 1 is actually nothing as, let's write it this way, is lambda minus 1 nu rho gamma rho. And therefore, when I substitute it here, I will get d lambda over d epsilon, lambda minus 1, product of these elements. And then within this is mu and nu, multiply with gamma nu. This is what I get. And this is, if you substitute here now our solution for this one parametric subgroup, so this expression, to the right-hand side, compute d lambda over d epsilon multiplied by d lambda over d epsilon multiplied by lambda minus 1. What you will get is simply the result will be eta mu rho omega rho nu multiplied with gamma nu. And so in this way, equation, which I think I will be finishing in the next lecture, takes the form gamma mu with x is eta mu rho omega rho nu gamma nu. And so this is an equation for x, which I need to solve. This is purely matrix equation. So all elements here are matrices. So gamma mu is a matrix and x is a matrix. And this equation tells you that the commutator of these two matrices is another matrix on the right-hand side, where omega rho nu are parameters of Lorentz transformations. Parameters of Lorentz transformation. So our solution for x, so what we are doing, we are solving for x. X is an unknown thing, which we need to find out from this equation now. Okay, I think my time is up for today, but if you have questions, I'm ready to answer. So this equation which will solve, complete the solution next time and find an explicit form of matrix S which performs the Lorentz transformation on the wave function psi x on our Dirac spinor.
So the equation for the matrix S is determined on the gamma mu, and you mentioned before that gamma mu can be there could be some unitary transformation and it will be the same. So also that won't influence the result of S matrix with different gamma mu, right?
So now we are not looking for transformations. I mean, you should distinguish. What we were talking about unitary equivalence of gamma matrices. Now, what we are doing is a different story. It's a different story. We are not solving for gamma matrices. Gamma matrices are considered to be fixed here. They are fixed and given. What we are solving for is a matrix S, which sits in the definition of this element x, s ds over d epsilon s minus 1. And so we are looking for a matrix S which relates the wave function in the Dirac equation in the transformed Lorentz frame with the Dirac wave function in the original frame. And so this is what we are looking for. What is this S? In terms of the original Lorentz transformation, relating the point x to point x prime.
Okay, I mean, in this equation, gamma mu is fixed.
Gamma mu is fixed. Yeah.
Yeah, fixed maybe could be regarded some parameter. And if
yes.
we change the parameter to another by a unitary transformation, we'll get another equation.
that will change, that will call the change of S by unitary transformation. Yeah,
so
if you will be changing gamma mu here by unitary transformation, this is of course possible. You can choose any set of gamma matrices to solve this equation, but this will lead to the change of S by the corresponding unitary transformation inherited from the transformation of gammas. That is true. Okay. Yes, that is true.
Well, and here, if I remember from some other books, S should be a spinor representation of Lorentz group.
Spinor.
Yeah,
use the word spinor. It's not spinor. It's spinor. Use the word spinor. Yes. Spinor. That's the correct pronunciation. Is spinor. And you are completely right. We will show that what we are deriving here is a spinor representation of the Lorentz group. And that is essentially what distinguishes scalars from spinors from vectors. All these objects, scalars, spinors, vectors, they transform differently under Lorentz group. And we can say they realize different representations of the Lorentz group. And these different representations of the Lorentz group characterized by such a quantity as spin.
Yes.
And probably spin, this is the origin of the word spinor. It takes its origin from spin. That's very important that now this object will describe for us physically particles which have spin. So it's a relativistic particles with spin, which we are describing. And these particles with spin will have a specific or particular property under Lorentz transformations. They will transform differently from scalars and vectors. And this transformation, this way they transform is exactly the spinor realization of spinor transformations of the Lorentz group. They realize spinor representation of the Lorentz group. That's exactly what you have seen in the books, indeed.
Okay.
And now we are deriving this. We are deriving this spinor representation of the Lorentz group, indeed. That's what we are doing mathematically.
Okay. Thank you very much.
Professor, this equation is valid for all fermionic spins. All right.
For all spins.
All fermionic spins, right?
What exactly do you mean by this? I'm trying to understand what you put in these words.
If it is like spin half.
No. It will be different. It's only for spin 1/2.
Yeah. Oh, for other type of spins like 3/2, 5/2.
It will be different. So you need then to redo the computation, because a relativistic equation which we are writing, the Dirac equation we have written down, it's an equation which describes a particle with a spin 1/2. If you want to describe the particle with higher spin, say 3/2, then equation will be different. The starting point will be different.
I think there will be like some 8 vectors then, column vectors.
Yes, there will be this will be then a different equation, and the wave function will be a vector spinor, because it will carry one index of a vector, and then it will be a spinor. So it will be column where each component has also a vector index. If you want to describe a particle with a spin, say 3/2.
Yes.
And that means that under Lorentz transformation, it will have different transformation properties. It will transform as a particle of spin 3/2, and that would lead to the construction. I mean, if you perform this consideration as we do now, it will lead to the construction of the representation of spin 3/2 of the Lorentz group. What we are doing, we are constructing representation of the Lorentz group of spin 1/2. 1/2, half, 1/2.
Okay. The Clifford algebra may satisfy or may not satisfy. It will.
No, Clifford algebra here, as soon as you are talking about the spinors, then Clifford algebra always appear. This is inevitable. As soon as you are talking about spinors, yes, Clifford algebra should appear.
Sir, what's the difference between Clifford algebra and the Grassmann algebra?
No, Grassmann algebra is different, because in Grassmann algebra, you have Grassmann algebra is a general notion where specifically you can say you introduce the variables theta I, and these variables satisfy, say, relations theta I theta j plus theta j theta I is equal to 0. This Clifford algebra, which we have introduced here, is different. We have gamma mu plus gamma mu. On the right hand side, we have 2 eta mu multiplied with an identity matrix.
So can we see the Grassmann algebra is a special case from the Clifford algebra?
I would not say so. I would still keep these notions different. I would say Grassmann algebra is one thing and Clifford algebra is another thing. I would not really mix them up.
Okay, thank you.
So Grassmann algebra is the algebra of anti-commuting variables. Clifford algebra is an algebra which has representation given by these gamma matrices, and which has this non-trivial right-hand side. So for a Clifford, it's important that you have this eta mu nu on the right-hand side. That's essential.
Clifford, I think, is used for higher dimension, right?
Clifford algebra, whatever you want to describe such an object as a spinor representations of the Lorentz group, then you need Clifford algebra. So Clifford algebra is used to build up spinor representations of the Lorentz group. The Grassmann variables, we come to them. They will be in our discussion, but later on, when we will be quantizing our theory, quantizing Dirac series, and Grassmann variables, of course, will appear. They will be, at the end of the day, components of our spinor. But the Grassmann algebra is a bit different story. So I would keep these two things separated.
Okay, thank you, sir.
Okay. Okay, if you don't have any further questions, then we continue next Friday. And we will finish with Lorentz transformations. And Lorentz transformations, I need also to explain to you something about parity and time reversal, how they act on spinors. And then we will study a particular class, very important class of spinors, which are called Weil spinors. That is what is the program we will be doing in the next lecture. Okay, if you don't have questions, then I wish you a pleasant day, and we will hear each other next Friday.